So, welcome back. New semester, new host, new speaker. We start with Katie Oliveras from Seattle University, from the US, all the way from the US. And she's talking to us about measuring waves using pressure. Thank you very much for coming here and being such a wonderful guest so far. And you won't disappoint.
Well, I don't know. I mean, well, now the pressure's on. So I want to thank you so much for coming today and all of the conversations that I've had so far. This has been a really wonderful visit. So yes, I'm from Seattle University. Just a little bit about my university. We're a small undergraduate liberal arts school. So we have no graduate students. We have no postdocs. So what we do is we just end up treating the undergraduates like they were our PhD students and hope they make it through. But I want to tell you about this project that we've been working on. It actually kind of accidentally happened at a pub one night. But that's how any good project is going to happen. I joke. That's not true. Don't go to pubs looking for projects. But, you know, it was a nice project that actually kind of involved all these different areas an applied mathematician enjoys, right? There's some pure math that, you know, proofs that had to go along with it. There was some application, and then there was actually experimental and field data validation. Like, how often do you get to do all of those in one project? And it was a real joy to work on, and we're continuing to push this. So I want to talk to you a little bit about it today. So while we have completed like the first part, a lot of the stuff I'm going to sort of allude to is a work in progress. So this is my disclaimer that, you know, I'm not going to have all of the references because, again, this is a project that just kind of naturally evolved for us. So we didn't have a very, you know, deep background in the area. So if you see any connections to areas that you're familiar with, if you have any references, suggestions, ideas, ways to extend it, ways to make things cleaner, please, 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 you know, let me know. And so I definitely encourage any feedback or comments that you might have. All right. So in general, what kind of problems am I personally interested in? And there's a lot. I am generally interested in free surface waves. So water, generally I assume it's inviscid and irrotational, so the nice, easy kind. I have a free boundary. And so I'm interested in using the governing equations to answer some important questions like what applications would benefit from actually using the fully nonlinear, use nonlinear in quotes, fully nonlinear in quotes, full dispersion model for water waves. I know that those full models are very computationally expensive. So is there a way that I can, in real time, measure data and figure out which appropriate asymptotic model that I could use at any given point? What if I want to measure states in the ocean, but I can't measure all the data? How can I reconstruct information from partial observations? And we'll talk a little bit about that. That's kind of the project today. And then I'm also interested in these stability questions. So turns out that water waves, at least as modeled by Euler, all seem to be unstable. So why do we see waves in the real world? So I'd like to know more about how the mathematics actually tells us how they are going to evolve or what happens in the sort of nonlinear regime as we look at the models. Okay. If I'm feeding back, if I need to stand somewhere, let me know so I don't echo back. All right, so I'm actually going to skip this outline because I say we just dive right in to talking about the problem that I'm interested in, or that we'll talk here today about. So in the US, part of our tsunami reporting or warning system is this DART network. And what you have are pressure transducers that have been dropped off at the bottom of the ocean. They're so deep you can't even see them on the slide. And when an earthquake occurs, what happens is these pressure sensors start sampling at a high frequency rate. And what they're doing is they're measuring the pressure, trying to figure out what's happening up here at the surface. So is there a wave passing by? And if so, can I use that as an initial condition in a forecast that could potentially help me warn specific coastal regions if a tsunami is approaching? And you can think about it, you know, You really want a nice fine-tuned warning system because the more times you try wolf, the less time or the less likely people are to actually evacuate when they need to. So you want a very nicely tuned warning system, and it all starts with measuring what's going on out in the ocean. Now, spoiler alert, the method they're using is actually a very linear model. It doesn't have all the full nonlinearities. It's not in the deep ocean. That actually works perfectly fine. And I'll show you that in experiments. It's just when any sort of measurements are done near shore, where the water gets really shallow, the waves get very steep and start to break, but things really break down. That might be a little too late for a warning system, but it's definitely useful in terms of measuring forces that impact your beaches, erosion, and perhaps developing seawalls that are appropriate to withstand those forces. So that's kind of the cartoon of the problem. I'm not talking about the forecasting part at all. That's cool. I'd love to be involved with that, but that's not what I'm talking about. I'm talking about, again, this very first step. Take pressure, turn it into a measurement for the wave height. So here's the cartoon of the problem. You can do this in higher dimensions with different, directions, etc. But let's just take the simplest sort of place to start, because that's what my applied math professors always said. Keep it simple, So let's start here. I have a pressure sensor at the bottom. I have a wave that's passing over that pressure sensor, a one-dimensional surface. Given the pressure at the bottom, can I construct the wave elevation? So that's the question. So, okay, first critical step here in the DART system is measuring the wave. So I like simple explanations. I like simple equations. I like going back to, I was going to say kindergarten, but I guess it's maybe, middle or high school. I'm not sure what the appropriate terminology is here, where you learn about hydrostatic pressure. That, hey, if I have water and I have pressure here, I can tell you something about the height of this just based on pressure equals rho GH. Cool. So, yeah, that works great. This is your hydrostatic pressure. G is the acceleration due to gravity. Rho is the density of the fluid. So if I knew pressure, I could solve for H, the height. That's hydrostatic. Things are still. What happens when things start moving? In case you're not aware, tsunamis move incredibly fast. If you took off in a plane from Japan and had a tsunami traveling in the same direction, I believe it would be a close race to who would end up on the west coast first, the plane or the tsunami, if it traveled the entire distance at the speed it does in the deep ocean. They travel fast. The faster things move, the more we're going to see like an impact on the pressure. So let's see if we can go beyond this. From here on, so now I'm just going to introduce some variables that I'm using. So H is going to be the mean depth. Eta will be the deviation from that depth. And here I have eta as a function of x, but in reality, right, it's a function of x and t. It's going to be changing and have different positions or different heights at different spatial locations and at different times. So now the question is, all right, if I had been given that pressure, is this pressure equals rho g? Now it's eta plus h, a valid model. Okay, well, let's just see. Let's solve for eta. And then let's plug in some data and see what happens. Okay. So this is the point where I get to introduce my collaborators. Bernard DeConnick was my PhD advisor, and one day we ended up just working on this project after I'd left. Diane Henderson is in the math department at Penn State in the US, and she has her own wave tank, which I love that she's in a pure math department. She has a huge two-dimensional wave tank and then an incredibly long one-dimensional wave tank. She has a whole basement for her setup. And so all of our experimental data comes from Diane. And Vishal Vasan, who was a graduate student at University of Washington at the same time I was, and who has been my partner in crime on a lot of these problems. Here's a picture of Diane's lab. So I want to show you a little bit about how we're going to do the setup so you can see how we're going to measure things and how we're going to validate them in the laboratory environment. This is the one, we call it the one-dimensional wave tank. And so you can see it's pretty long. And in this wave tank, what we have are different pressure sensors that are installed along the bottom of the tank at very discrete locations. I believe there are 5 different stations along the whole length of the tank. And you can kind of see one of them right there. They're drilled in to be as close to flush with the bottom as possible, an idealized setting, or as close to an idealized setting as we can get. You cannot see it probably, but there are 2 little fine wires coming down here directly above, or sometimes a little off to the behind those pressure sensors. These are surface capacitance gauges. They're going to allow us to measure the free surface height simultaneously. So this allows us to do our validation. We'll get both pressure measurements and we'll get surface measurements. And so the goal is to go from one to the other. I did not bring popcorn, but I apologize. I'm not going to make this video larger, and I'm only going to run it for a second because we did not have the steadiest hands when filming it. So it's a little jumpy, but you'll see the kind of simple waves that we start with in our experiments. And I may have some more group packets in the slides later on. I can show you that we did as well. We don't have videos of those. All right, so you can see it's a little jumpy. But right now we just have a periodic wave train going down the tank. Beautiful, right? Look at those waves. Of course, we can control it, and we can do some limited control on generating various specific profiles we want, but we just have a single plunger, so there's limited things we can do. So yes, those are waves. We're going to take one of these. In fact, we're not going to take this sequence. We're going to take one that was just a single push. So you'll see a primary wave followed by a dispersive tail behind it. And we're going to use that to test our hydrostatic pressure. So here's some data that we get. Here's our pressure sensor data. So this is pressure. This is, here we have our surface height measurement. And our goal is to take one of these, or a region of this, and see if we can go from that pressure to the measure wave and see how close of an approximation we get. Okay, so this is all just setting things up. I should say that there are some cheats that I'm going to employ. So I told you there's pure math, there's applied math, and there's, well, let's just say things that an applied mathematician might feel uncomfortable doing will be done along the way. And one of those is the following. I cheated. I get a time series. I have a single pressure measurement at a point, and I get a time series there. I'm going to treat it like a spatial series for my first application, for the first way we're going to approach this problem. Meaning I'm just going to take the wave speed that approximately that, hey, this is a stationary wave, or this is a traveling wave, stationary in a traveling frame, moving with approximately this speed. And so I'm going to make a time series into a spatial series. So this is no longer time on the horizontal axis. This is subspatial measurement, which is a little, doesn't feel good. Okay. So I've taken one of those regions here. It might not have been for this exact experiment. This is actual data. It looks like a cartoon, but just use the data points to actually show it on the screen. And now I'm going to take that hydrostatic approximation. I'm going to show you what you would get. You would get this. So even though those waves going down the tank didn't look that nonlinear, I mean, they didn't look super peaked and pointy, you can see that if you just use pressure equals rho GH, your error is on the order of 15% if you're just considering the peak height. You'd like to do better than that. I mean, especially the last thing you'd like to do is underestimate a peak height. I mean, maybe a little bit of an overestimate might be okay, but we're underestimating significantly. So how can we do better? And how can we do better in a way that captures as much of the nonlinearity in the problem as we'd like, but without being computationally expensive? It's that delicate balance there.
Sorry, can I ask a question?
Yes, please. Oh, yeah, and everyone, please interrupt.
So, aren't you missing also a term that depends on the velocity?
Yes, that is a great question. I'll show you some sneaky ways to get around that. And you're right, like technically, even the use of C equals, square root GH is a bad approximation in these regimes where you're far from the linear limit. Turns out that you can show later on that it can be formulated by, sorry, let me see how I want to articulate this. You can formally eliminate the velocity totally from the problem, which kind of surprised us. We started first by doing sensitivity tests. Like, what if I picked a different velocity? What if I guessed a velocity? And we made those guesses pretty wild, and it was still converging. So later on, we realized, oh wait, there is a formal cancellation. But it's due to some assumptions we had to make, and assumptions that seem to work. Good enough. Did that get it?
Yeah.
It basically, I'm like, hang on, wait, I'll show you some more as that.
No, I thought that in the formula, I mean, aside of moving with a wave speed, with a feather speed, don't you have for the pressure also a term that depends on Bernoulli? So it's
Yes. Okay, that we're going to eliminate. Actually, that's going to be the glue that brings everything together. And that's exactly right, yeah. Okay. So we'd like to do better. We're going to use Bernoulli to glue everything together. So here's now let me put my assumptions in. So for the first way we're going to approach the problem, again, assuming one-dimensional free surface, I have constant density, there's no friction boundary effects, it's irrotational, so no vorticity, it's inviscid. I have a traveling wave moving with a constant speed, so that just means if I'm moving with the wave, nothing is moving in my frame of reference, and I have a flat bottom. Most of these things can be relaxed, with the exception of vorticity, which even just simple constant vorticity causes all sorts of challenges. So most of these, though, we can relax. All right, so here are our equations of motion that I'm working with. So I'm just starting with Euler's equations inside the fluid domain. So I have essentially conservation of mass. I have my conservation of momentum here. So this in an irrotational fluid is going to essentially become my Bernoulli equation. U here is the velocity vector, so little u is horizontal, little v is vertical velocity of the fluid. These two equations are posed within the fluid domain, and then I have kinematic boundary conditions, basically saying the geometry of the velocity, or the geometry of my domain and the velocities are related. So no water's going through the bottom. So that means vertical velocity is 0 at the bottom. And of course, the time rate of change of the free surface is going to be pushed essentially by the velocity in the normal direction at the free surface. The last condition is a little different than what's normally written. Usually people will say that the pressure is equal to 0 on the free surface, or it's constant atmospheric pressure on the free surface. We could put localized pressure if we want, but let's just go with constant atmospheric or 0 pressure at the free surface. And rather than writing that as P equals 0, I'm writing that as the derivative of the pressure along the free surface is 0. There's some just nice bookkeeping that happens later on with this. Since I'm assuming it's irrotational, I can use a velocity potential formulation. That means there's going to be a potential such that the gradient of it's going to be u. So that gets us to Laplace's equation. So I have my potential, v, and the gradient of which is my velocity in the fluid domain. Here are my two PDEs inside the fluid domain, my kinematic boundary conditions, and the kinetic boundary condition, or the pressure boundary condition at the free surface that has now been integrated, and we used our momentum information to get there. So this is again pressure equals 0 on the free surface. Here's my system. Now what I'd like to do is figure out how do I take pressure measured here and get the free surface measured there. And first thing we're going to do is that traveling coordinate frame. So my time derivatives are now going to be replaced by minus c times a spatial derivative. So I'm going to be going from x to x minus ct. And in that frame, the time derivatives are now 0. So I hope I got all my time derivatives gone. And now my goal, again, is to take information here at the bottom, connect it with the top. And so what I'm going to do is look at this and say, well, let me start by looking at the Bernoulli equation here in the bulk, but now evaluate it at the bottom. So just take z equal to minus h. This is going to be a really easy setup. If I take z to be minus h, what happens is the phi z squared is going to disappear because of my boundary condition at the bottom. And I'll have a phi x squared here, I'll have a phi x. This will be pressure at the bottom. This will be, you know, minus gh. There's a rho somewhere in here that disappeared. Okay, rho is 1 for water. There we go, done. The thing is once I do that, I realize, wait a second, this is not a quadratic equation. When I say this is an easy setup, it's an easy setup. This will be a quadratic equation for the horizontal or tangential velocity at the bottom of the fluid. And I can solve that in terms of the pressure. That doesn't seem like it's going to help or do anything good, but look at the free surface. Now, I do have a phi x squared and I have a phi z squared, or phi z, however you want to say it. I can solve that here, my kinematic boundary condition, plug it back in. Okay, that's going to now exchange my phi z for phi x. Another quadratic equation in phi x. Like, it's you know, elementary algebra. So this is the simple game. We're going to take our Bernoulli equations, write them simply in terms of, we're going to say, hey, look, I'm going to write the horizontal velocity in terms of the pressure at the bottom and in terms of the free surface at the top. And all I need to do is stitch them together with the solution of Laplace in between. That's the whole game. Yeah. That's a great question. Since I'm irrotational and inviscid, it's going to be the same constant throughout the fluid. So I can push that into my phi t.
And now it's in this form. I was just wondering, if you go off to the left, so it's minus infinity.
Then I can always absorb that in, and because everything's only going to rely on a spatial gradient or a horizontal velocity, it's never going to be a problem for me. If I had, okay, so let's say I have quiescent back, like at plus and minus infinity, I have maybe 0 elevation of the free surface and maybe either a constant velocity or a 0 velocity at plus and minus infinity. In that case, I don't have to worry about any sort of jump conditions or anything like that. Periodic is fine. If I do have more complicated end conditions or a finite domain, it's not the Bernoulli constant that's going to be the trouble. It's really going to be more about how I prescribe the boundary conditions appropriately and incorporate them in. So you can, in the irrotational and inviscid, always eliminate the Bernoulli constant as long as you're careful and don't ignore mean flow. And this is going to capture mean flow. But I can go through the details a little bit more. It gets a little bit, you have to be a little careful, but yeah, you can always get rid of the Bernoulli constant. Other thing. Okay, I'm just going to put it all together. Look, actually, I'm going to skip this, so bear with me. Look, I solved a quadratic. I remembered my plus or minus sign even. That's great. This might seem like it will be a complication because I've got this plus or minus sign. So here is the velocity, the tangential velocity at the bottom minus the wave speed. It's going to be plus or minus the square root quantity that depends on the pressure at the bottom. You may think, well, plus or minus this can be troubling, but because I have a maximum principal argument, I know that if it's plus at the bottom, it's got to be plus at the top. I've got an irrotational fluid, so I'm not going to get a sign change. If I have a rotational fluid, like if I have vorticity, then I could have a sign change. And there's not really a good way to tell if I have a sign change unless I'm able to measure the entire velocity in the column. And that's not quite feasible in some of our applications. Okay, so here's the quadratic equation solved at the bottom. Let's do it at the top. Here's the quadratic equation solved at the top. I even highlighted my unknowns, eta. So remember, it's given pressure, find the free surface. So I have the velocity potential now in terms of this. So putting it all on a slide together, here are the gradients in terms of my knowns and unknowns at the bottom and at the surface. And so I take my pressure sensor data, I take my wave height, and I'm going to connect them together with solutions via Laplace equation. So that's all I need to do is write down a general solution use the data at the nice flat bottom, that's nice, to figure out any unknowns or those sort of constants that show up in front, and then evaluate that solution along the free surface and get my relationship. So I take my Laplace's equation, I'll just write down a general solution. I'm doing this on the whole line with decaying boundary conditions because that's the easy one to do in front of a live audience. I can write down my general solution. There should be, no, this is right, in this form. And so to figure out what this unknown is here, I, of course, take the x derivative. I'm going to plug in z equals minus h, and then I will use the pressure data. That pressure data will then allow me to solve for this. Once I have that pressure data, I know the solution. I take the x derivative minus c, and then evaluate it at the free surface and relate the two and find data. Yeah?
Can you just clarify, so here you haven't made any assumption about linearity
Nope.
or any...
Full nonlinear. This is capturing everything in the nonlinear regime for traveling waves in 1D. So yes, there are lots of simplifications, but we definitely have the full nonlinearity. In fact, when you plug all of this in, you find that your solution or your potential takes this form where, again, you know this pressure data, and you can write everything in terms of Fourier transforms or pseudo-differential operators if you like. And so now we just go back and we take that, we take an x derivative minus c, and it turns out to simplify as this. And that has to equal that boundary condition we had set. And that's it. That's a fully nonlinear relationship between pressure at the bottom and the free surface for a traveling wave solution in 1D to Euler. It looks horrible, okay? I mean, not even just bad from a, kind of understanding it kind of way. This curly f is the Fourier transform of this quantity, by the way. It doesn't just look hard in terms of getting any information about it. It looks hard computationally as well. I mean, think about any noise in this pressure data. Any high frequency noise, I have this caution K. That is bad. So there are some problems here that I'm going to have to be careful with. Turns out we can do some things with regards to that. Just as a heads up, I could write this in a more compact form, kind of thinking of it as a pseudo-differential operator. It looks cuter, but it's still as horrible as it was. So what am I going to do with the next 15 minutes? Because I'm going to try to end right at about, 2:45. So in the next 15 minutes, I'd like to talk about, well, how do you actually do anything with this? How well does it work? And what happens when I use this in those experiments? And maybe this is going to be a pain to solve because I have to basically plug in data for P here and use some sort of nonlinear Newton's method, whatever sort of nonlinear numerical solver you would like to use to solve for data. It's not pretty. So maybe instead I'd like to do asymptotic. So maybe I'd like to then start looking at approximate relationships. And that's where we're going to start. Before we do any sort of nonlinear solving on this, let's just look at some approximations we can get out. I am going to skip some information about the proof for the sake of time, but I will say that one thing you should ask yourself, so this is the mathematician hat, which is, hey, you wrote down this really ugly map between these variables. One, is it actually even solvable? If I get pressure, if I put some pressure data in, can you actually even solve for data? And then second, is it a unique solution? Third, is that solution even a solution to the water wave problem? And we can answer affirmatively to all of these things. Initially, our proof was just for small amplitude solutions. So the proof itself relied on some measures of smallness, but I believe it was later extended to go all the way up to limiting waves, limiting height periodic waves, so the steepest you can go via some sort of a bootstrapping argument along the bifurcation curve. Not going to go into that. I'm going to skip kind of that outline. Let's go to the asymptotics. So to do the asymptotics, we need to introduce some small parameters. So I'm just going to non-dimensionalize. For those of you in the waterways community, these are your standard A over H. So it's a ratio of the height of the wave to the depth of the fluid. So that's epsilon. H over L is basically like a vertical to horizontal aspect ratio, H being the depth of the fluid, and L being the wavelength. And so we'll non-dimensionalize, we get rid of gravity, yay, and we end up with this equation. And so one of the things we can say is, well, what if I actually want to solve for small amplitude solutions? Well, small amplitude, epsilon small, I could expand an epsilon. What if I want to look specifically at certain kinds of waves where there's a balance between the horizontal scale and the vertical scale? Then I could make a balance between epsilon and mu and expand in that parameter. And I can see what happens in those different regimes. So that's what we're going to do. We'll start with the easy one. We're going to assume what I call the shallow water conditions, which means if you're familiar with KdV, this is the KdV balance. I'm going to take epsilon to be proportional to mu squared. And I'm going to expand in powers of epsilon. And at leading order, remember this is non-dimensionalized, I get eta equals P. Now, if I'd gone back to the dimensional variables, this is pressure equals rho GH essentially. Okay. All right, so I get the hydrostatic approximation. That's a good sign. Anytime you come up with something new and wild, you should make sure that what you know is already embedded in it, and sure it is. Good. I could go up higher order terms, and now I get a differential equation. So once I start going higher order terms in those expansions, I start picking up k's because of the cosh k, which then get interpreted as derivatives. And so that's how I end up with these derivatives on my pressure. So given pressure, I can evaluate these. Those are spatial derivatives. And I can reconstruct what the free surface is. Again, this is a KdV type balance. I want to point out, so going back to your question earlier, in this case, the wave speed C does show up. And so this formulation is most likely sensitive to having the speed of the traveling wave be approximated well. If you just have one pressure sensor, you're not going to be able to get that speed. Even if you have two, you're not going to be able to get, honestly, in the wild, you're not going to be able to get that speed. So that's a downside of this. Okay, let's just make epsilon small and see what happens. If I only let epsilon be small and I keep mu as a fixed parameter, then at leading order, what I end up with is this relationship. So eta of x is going to be the inverse Fourier transform of the Fourier transform of a pressure data. So take your Fourier transform, hit it with this cosh of k. In dimensional variables, that would be cosh kh. Invert it, and that will give you your pressure. If you then chose to expand this in powers of mu, you're going to pick up k's, which will give you those differential equations we saw before. Okay. All right, so this is actually a well-known transfer function approximation. You could go higher order as well and have the next correction to this. It ended up getting its own line because it was just not pretty. So this eta 0 is going to end up being this first correction here, and you can write the second correction in terms of it. Yet again, we see C popping up. That's not nice. Okay, we have, let's see, like 8 minutes left, which is just enough time for me to do some bad applied math and see what it'll get us. So we're going to take those 4 different asymptotic formulas. We're going to take one more. And this one was born out of pure laziness in waiting for the numerical method to converge with a full nonlinear solver. We're going to expand this in epsilon. We're going to do a small amplitude expansion, but we're only going to expand in some of the epsilons because we'll say, look, epsilon is kind of telling me, if I'm assuming epsilon small, it's kind of like I don't know that value, but I know the full pressure. I have this measurement. So I'm not going to expand in this epsilon. I'm going to freeze it, and I'll expand in the epsilons in front of my etas. When I do that, I'm going to get an expression that I can actually solve. It's going to be a linear expression for eta. I can solve that in terms of the pressure, and I will get just a fraction. And now I can't remember if I have that here. Darn, I don't. But if I do solve it, oh, I do. Notice I'll get an epsilon here in the denominator, but I end up with this relationship. By the way, if I did a geometric series expansion, if I assumed that this term was, small enough and expanded, the first term, that would be the same as the transfer function. So it's kind of like I'm somehow, modulating this transfer function. Again, I only expanded in that epsilon, the red epsilons. Once I solved for eta, I actually did expand in one epsilon more. Time later, I expanded in this one just a little bit and did another linear solve. Again, this is not good asymptotics. My asymptotics professor was very upset until he saw the results. It works amazingly well. And we had no justification for it other than laziness. Luckily, I believe it's David Lenz who later came and proved that it ended up being the 3/4 potty approximate of the full time dependent problem. So luck. I mean, really just luck. All right, so here to close things out, let's actually take a look at those asymptotic formulas. We're also going to do a full on Newton's method with the nonlinear, the fully nonlinear equation. We're going to look at numerical data, so numerical wave tank experiments. We'll also look at the physical wave tank experiments, and we'll close out on that. All right. There's some graphs missing, I'm sorry. Let me tell you what we're about to look at. So if you go back to that first plot where I had the nice hydrostatic approximation compared with the real wave, what I'm going to do here is take that relative error in the peak. So how far off percentage-wise was I in determining the peak? I'll try to explain what each of these acronyms are. They came from the paper because the table was hard to regenerate. So shallow water, order 1, this is hydrostatic. So the first column should be bad. We know from that first example, the error was about 20% in one of those. And you can see out of these, I think it was 9, you can count them. Out of these experiments we ran, the error did persist around that same mark. We ran 3 different depths, and we ran them multiple times each. And so in that case, we had this error. All right, the transfer function, the one where we only expanded in epsilon but kept mu, does a lot better. And you can think about it because you're kind of picking up more of those frequencies, and they're, I don't want to say interactions, but you're picking up more of the frequencies, the nonlinearities. Okay, so that's the transfer function. Now we have the shallow water order 3. So this is like the hydrostatic, but with 2 extra correction terms. And you see the error is getting better and better. I mean, this is pretty good. But there's still some challenges with this one because it involves all those derivatives. And if I have noisy data, I'm kind of shooting myself in the foot a little bit. All right. This is the next correction to the transfer function. So not the one I showed you. But you can see this is doing really well. But this actually turns out to be a bit more computationally expensive than what we had here. This, by the way, the transfer function was nice because it was a forward Fourier transform and an inverse Fourier transform. That was all the computational power you needed. With some filtering, because your data might be noisy and blow up. This one's fun. This is this bad asymptotic small amplitude approximation question mark H. The question mark is I have no idea what order to say, but I can say H for heuristic. And so that's what goes there. Holy crap. It does really well. Wait. The last one is the full nonlinear. It is a challenge to solve the fully nonlinear equation because it's a horrible integral differential equation with nonlinearities all over the place. You have to be very careful with whatever method you're using. But we did with some very, very clean data. And just comparing these two, kind of remarkable. 0%. It's to the precision that we had here. Okay, so don't yell at me too much. But look at this. This is remarkable, the relative error here. And this was only 1 forward Fourier transform and 2 inverse transforms. It's very, very, very fast. This is an iterative nonlinear solver. So, I mean, it's kind of remarkable how well it does. Again, we can push these experiments even harder, like make them more steep, make them, less traveling wave-like. And of course, these will start breaking down in different ways. But one thing I forgot to mention about this one, C dropped out completely. So the wave speed ended up completely dropping out. And that was one of our first hints that maybe there is some form of cancellation. And there is. But I didn't present that one here. So on the heuristic one, we did not have to make any assumptions about what the speed was. So that's pretty good. It's computationally efficient, and it seems to do really well. And so I'll just wrap up here. Oh my gosh, right on time, I think. With going back to the cartoon and looking at just this one experiment. Here was that hydrostatic approximation from earlier. And so you can see, okay, that relative 20% error. And here's the heuristic. It's not perfect. You can see there's some issues here. There's some skewness, some kurtosis that isn't being captured. So it's not perfect. And again, we're just using our metric we chose was the peak wave height. That was chosen before we got everything working. So we should probably look at other things such as width as well. But the eyeball metric at least looks pretty good, and it's very computationally efficient. And so with that, I will go ahead and close and wrap up and say thank you for your attention. Please, let me know if you have any questions or comments. I didn't get to the new stuff, but I will say one of the exciting things that we're doing right now is a full-on time-dependent version with a single time series. And what's remarkable about that is, one, you can do it in the first place. Two, you can kind of do some strange asymptotics yet again, and get things that are accurate to maybe quadratic or even cubic order, yet are still linear computations. So it's kind of remarkable, some of the things that come out, and I'm really excited about that work. And if you're interested, I'm happy to talk to you about it. With that, thank you. Did it right on time.
Thank you very much for the very nice talk. I really enjoyed that. Question time. We have a few minutes to roast Katie.
Yes.
Not ready.
Oh, no, bring it. Bring it.
Can you just go back to the table of all the
Yeah.
error there? So it seems that there's some sort of correlation between the errors, and I'm guessing that all your approximations are approximating the fully nonlinear version rather than the experiment.
Wait, I might not understand the last part of your sentence.
So all of your approximations are approximating the sort of model equations that you've written down, which are being solved exactly by the nonlinear solver. So have you tried comparing all those approximations with the nonlinear solver solution?
Oh, yes. That's a great question. I don't know if you noticed, I was shocked when I slide transitioned earlier because I was like, oh, I took those slides out. Yes, we have. And one of the things we looked at also was the region of validity for each of these asymptotic solutions. So push, for example, the amplitude of the solution higher and higher and higher. So that would mean I would need more of these small amplitude corrections to be present. And as I push it higher and higher and higher, each one of those model equations breaks down into different regime, and you can see exactly how that correlates. It looks very similar. Actually, maybe a little bit more dramatic.
So I was thinking with the SOA question mark column, the larger discrepancies there, is that because it's basically agreeing with the nonlinear one, which also has those same larger discrepancies?
Yes, exactly. In fact, if you look at this numerically, these are both on the order of 10 to the minus 16, which is weird. Like the fact that this is so close, until you get to really, really large amplitude. But the fact that this tracks so closely.
So that's doing a really good job of approximating the system, and it's the experimental stuff that's out in those cases. Exactly,
and it's fast. I mean, how can you not feel good at the end of the day? But yes, I understand. That was a really good question. Any others?
Questions?
Too harsh. Oh no, bring it. Like I said.
So the Fourier transform is on the space variable.
Yeah. That's a problem. Yes, it is on. You're right. In a sense, I kind of cheated when I said we were able to formally eliminate C. In terms of the reconstruction formulas, yes, but I did have to go to the spatial. I had to take the time series to the spatial resolution, which involves C. It turns out that you can also put that wrong, like garbage in. I could put like 40 to 50% error, and I'd still get these kinds of results.
Or you could have a series of pressure gauges,
Yes.
and then do that.
Yeah. But in that case, you would definitely want to make sure your wave was directed.
Sure.
So in Diane's tank, it would be perfect, but in the wild, it would be hard. But yeah, that's a good point. I should have been a bit more cautious about that. With the time series, we can eliminate that.
And the error is on the crest.
Yes.
Set.
Yes.
So it's not on the norm.
Correct.
Okay.
Correct. Yeah.
It's impressive.
Thanks. Yeah.
In your fully nonlinear equation for the surface elevation, you expanded in epsilon, which meant that the amplitude was small. Is it possible to get anywhere by flipping upside down, assuming epsilon's large and expanding in 1 over epsilon? You get larger amplitude stuff.
I have never thought of that, and I have no clue. I am not going to answer that question in front of people because I'd like to think about it first, but that's interesting. Yeah, I haven't thought of that. I know that there are challenges, mainly because everything assumed this periodic traveling, well, not periodic, a traveling wave. And if it was periodic, I do know there is a relationship between the speed and the amplitude, and everything's nice and well behaved for small, finite. When I get up to what this limiting area is, I'm kind of leaving it not drawn in because I don't know exactly how it's going to look. But this is where you get your limiting, your most peaked things, and that's hard. Like, so you're kind of trying to expand about something that's not smooth. So I don't know.
Thank you.
That's as far as I have gotten in terms of thinking about what you saw.
I have a question.
Yeah.
So you present the work and it's biased towards shallow water, right?
Yeah.
If we move towards intermediate and deep water, so you like your epsilon becomes the ratio between like the Ka, so the like how does it go down?
Yeah, so also in those same numerical wave tank experiences, that's one of the things we looked at as well. And when you're in deep water, it's pointless to do any of this. This is going to be great. This will be even better, and that's enough. It's really when you're near shore or in those shallow regimes or where you have the very strong nonlinearity that you need to do something really more. So this is why dark sensors can get away with hydrostatic pressure, because in that scenario, it is. Yeah. The delta you would get with the extra computation isn't worth it.
Thank you.
Yeah.
I was just wondering whether you, obviously, one of the key applications is the tsunami, where you're around the world. Do you have any sense of how things like stratification would play a role in the ocean? Because that's going to really mess up like how your relationship.
Yeah.
Or are you just looking in cases where stratification is not really a problem?
So that's all we looked at with this method. The time series version that I alluded to but didn't talk about came about as a happy accident with this other like little pet project of mine. But what's interesting in that case is you can do, we've never done continuous stratification, but you can get somewhere with these sort of, layers. And it's really fascinating because now not only can you get, information about moving how pressure goes up, if you will, to the free surface, but also how the different layers interact. And so you can do inconsistent asymptotics there as well and get some interesting information about the interaction between different layers. That's something I'm hoping at some point to look at when I find time. Yeah.
So what do they actually use on the field for this?
So in deep water, it is hydrostatic. So out those dark buoys that are out in the middle of the Pacific, those are going to be using the hydrostatic. When you get closer to shore, so things off the coast of North Carolina, for example, I do know that those are using not this transfer function, but what's interesting about it is it's a transfer function divided by a fudging factor. It's interesting because, you know, this was the transfer function divided by something that it wasn't a constant fudging factor, it had this sort of KH involved. But in certain regimes, this looks almost exactly like that. Almost exactly like that.
I wonder if the fudging factor has something to do with the filtering of the data.
Yeah, no, exactly.
That would be my guess.
Oh yeah, no, I absolutely imagine so. I know we've been talking with Army Corps of Engineers about implementation of this in some sort of trial scenarios that they have, you know, these nearshore sensors, just to see like, okay, we've done it in a lab, we've done it in a couple of, you know, like, let's actually see, does this really, really perform better in the wild? So yeah. That answer? Okay.
Okay. So if there are no more questions, we can thank Katie also. And, yeah, that's it. Thank you for coming. And
Yeah.
you're welcome to stay for coffee or as long as you want.
Is it as much coffee as I want? That's the question.